We're going to learn the next thing on the molecular geometry worksheet. We have learned how to do Lewis structures. First of all, how to count the number of valence electrons, how to do Lewis structures, how to come up with the correct geometry code, which has to do with how many atoms are attached to a central atom and how many lone pairs there are on the central atom. And today, we're going to, first of all, build the models for each of these molecules. I have the model kits that we're going to be using, and they are color-coded for elements. So you can refer to this color-coded list. I'll talk a bit more about that in just a tiny bit. But we're also going to do some simple calculations to determine if the bonds in these compounds are polar or nonpolar. Now, if you go back into, I don't know, about a week ago, when we began talking about the two types of covalent bonding, we indicated that there was polar covalent bonding and nonpolar covalent bonding. The polar covalent bonding, remember, has one element in it that has a little bit stronger pull of electrons toward it. And the reason it has that is because it has a stronger electronegativity. We learned that electronegativity was the attraction of the shared electrons in a compound between two atoms that are sharing electrons. And I gave you this within your packet. I've taken yours away from you. Went to that page. This is an electronegativity chart. Okay? Now if you go to the next page, we did some practice that day with looking at the differences between electronegativities of the atoms that are bonded to each other. And depending on the differences, it placed that bond into a category. It placed it into either polar covalent, nonpolar covalent, or ionic. Now, for the sake of this activity that we do today, we are going to do electronegativity calculations, and we're just going to determine if a bond is polar or nonpolar. And if the value of that calculation is either greater than or equal to 0.3, we will say that it's polar. If it is less than 0.3, we'll say that it's nonpolar. I'll repeat that in just a little minute. I want to do, there's no difference between a little minute and a big minute, but in a moment. I'm going to replicate this activity with a different compound, so you get a sense of what you need to do with this worksheet. So the first column is the number of valence electrons. The second column is the formula. Is that correct? Or is that so this is the formula and the number of valence electrons. Then we have the Lewis diagram. Then we have, it says type of molecule. And what I told you to do for that was to write the geometry code. For those of you that were gone yesterday, I'll review again what that means. Then there's an area where you need to make a sketch. And there's a whole bunch of information on there that you need to include with the sketch. So I'm going to go through an example of how to handle that. Then there is a question, are there polar bonds? Yes or no, and it tells you to show the calculation. I will tell you, I'll write up here, and maybe you should too, that if the difference is greater than or equal to 0.30, then that bond is polar. Yes, it is polar. In this activity, it may fall within the range of ionic. We are just going to categorize it as either polar or nonpolar. If it's greater than 0.30 or equal to, we say yes, it's polar. And then the next column is whether it is a polar molecule. Tomorrow we're going to discover that sometimes a substance can have polar bonds, but be a nonpolar molecule. Now, why on earth does it even matter? This concept you deal with regularly, and you may not even think about it. But the fact of the matter is, polar substances and nonpolar substances don't mix. So if you get oil-based paint on your skin because you've been painting, doing something artsy, all right, you get it on your skin, what do you use to remove that oil-based paint? I hear turpentine, gasoline. Some people use fingernail polish remover. Acetone, which is the substance in fingernail polish remover. Bleach probably wouldn't work. What you're using is you're using substances that don't mix with water, because water will not dissolve that oil-based paint, but other oil-based things will. All right? So nonpolar substances will dissolve nonpolar substances. Polar substances will dissolve polar substances. Say you get an ink stain on your shirt. All right, what are some home remedies for how to get the ink out of your shirt? I hear a club soda. I've never heard this. Maybe I have. Some of the inks are going to be a mixture of both polar and nonpolar substances. So you could use a series of steps. The club soda would probably, because soda is water-based, would probably take out the portion of the ink that is more water-like. Other home remedies for removing inks.
Toothpaste.
Toothpaste?
I'm serious.
I'm not sure if toothpaste is polar or nonpolar. It's a mixture of things, and I would like it if somebody could investigate that. Any others?
What's in the sprays, like the shout sprays you put?
Shout sprays? I'm not sure. Yep. Your soaps and your detergents are water-based. However, they're designed chemically to kind of surround fat molecules and separate them from each other and remove them from wherever it is. So they're kind of working differently. They're attacking the fat molecules and they're kind of carrying them elsewhere. All right, have you heard of this? Hairspray.
Yep.
I know you've heard of hairspray.
Yep.
Some of you may have even used some today or this year or this decade. I used it a couple times this decade. Not today. One of the home remedies for removing ink is to put hairspray on it, and then you blot it up with like paper towel or a cloth. All right, that may remove some of it, but it might not remove all of it. Other home remedies include rubbing alcohol. Dabble a little rubbing alcohol on it. Other home remedies include putting fingernail polish remover on it, the acetone in that to remove the ink. Sometimes if you take it through a series of steps, you can get all of the dyes of the ink out by one of those steps right after the other. The substances in those remedies, the molecules in there, have similar chemistries or polarities, nonpolar versus polar, as to whatever the ink stain is. So like dissolves like. After our test, we will do an activity in which we get to explore those concepts. It's total fun. It'll be a good time. So we'll learn how to determine if it's a polar substance tomorrow. Today we're going to do polar bonds. I'm going to choose maybe one that I haven't done today. I'm going to choose sulfur difluoride. I am not positive if this is an actual the right makeup to do what I need it to do. The number of valence electrons. The sulfur has 6, it's in group 16. The fluorine has 7, but there are 2 of them, so we're looking at a total of 14 or 20 electrons. With the Lewis diagram, I put the central atom in, and I attach the other atoms with single covalent bonds. I have just used up 4 electrons, which gives me 16 electrons left to distribute around this molecule in electron pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the next thing to do is to check to see if each element is fulfilled by the octet rule, unless it's one of the exceptions that we learned about the other day. But most elements, we want to see that them have 8 electrons. Fluorine has 2, 4, 6, 8. Sulfur has 2, 4, 6, 8. And this fluorine has 8 electrons, so they're all fulfilled by the octet rule. Now, I'm going to remind you that the geometry code, A stands for the central atom. X stands for the number of atoms attached. And E stands for the number of pairs of electrons on the central atom. Alright, A stands for the central atom. X stands for the number of for the number of atoms attached, which is how many? 2. And how many pairs do I have on the center atom? 2 pairs. 2 pairs. Alright, so I would write E2. AX2, E2. Now, I've given you this as a resource. I'm not sure where my extra ones are. And it's kind of a neat visual because it shows you atoms being attached. And this particular resource actually also shows you lone pairs. So you could find the picture that shows 2 atoms attached and 2 lone pairs, which happens to be right here. Or you could look for the geometry code, AX2, E2, which also happens to be on here. So it ends up that the shape of this molecule is going to be bent. Okay? So I'm going to draw this molecule quite big. I really don't want you to draw the molecule until you've built it. Let me build it. On my code, selenium is black, and I'm attaching fluorine, and I'm saying that fluorine should be yellow. Okay? So I'm going to put 2 stick bonds in 2 of the holes in this atom. That's the selenium. It's not selenium at all, it's sulfur.
It's still black.
Yep. I used selenium earlier today, and that's why I made that mistake. So sulfur is also black. It does not matter which way I build this, which of the locations I put it, it all ends up being bent. Some people may start getting crazy and wild and start saying, look at that, say, oh, well, there's one in the middle and there's 2 on either side, so it must be a straight line molecule like this instead. Okay? It's not. Because we have these 2 lone pairs, we have 4 things attached to this. There are 2 holes left in here. Some of the models you build today will have holes representing the location of lone pairs. Some of them won't. Okay? So it's a bent shape. Now the next thing is to indicate what the angle is. Now on this diagram, if you look at the one that's AX2E2, it doesn't give you an angle. If you go over this way, you'll see that if 4 atoms are attached, it's 109. Remember, if we have a pair of lone pair electrons, it will put a downward force on that and make it a little less than 109. If we have 2 lone pairs, it's less than 109. The good news is, you do not have to remember that, because if you look at this diagram right over here, it has it on there. I like this one for the pictures better. I like this one because it includes all of the bond angles. You have that as a resource. Yes, you may use this on the test, of course. I don't have them memorized. All right, what do we do next? What I want you to do next is I want you to, in the circle, indicate what element is there. So we have sulfur and fluorine. What I also want you to do is I want you to write the electronegativity value of each of these elements. I know that fluorine is the most electronegative element. What is the value of the most electronegative element? I will be surprised if anyone can remember, but I know that some people remember trivial types of things like this. Anyone remember?
What is the value of the what?
It is 4. How did you guess? The electronegativity value for fluorine is 4. It's the highest value. It was arbitrarily chosen. All right. What is the value for sulfur? It will say it on your electronegativity chart that I told you.
Oh.
2.5.
2.5?
Yeah.
Is that correct?
Yeah.
Is it right, Katie?
Yeah.
Well, it's right here. Is it
Oh,
2.5 for
children.
sulfur? So I'm going to do the calculation here to determine if this bond right here is a polar bond.
Somebody tell me I'm right.
Yeah.
Thank
You're
you.
right.
Thank you.
It has been confirmed that Katie is right, and it is 2.5.
5.
Wait for it all in those circles.
Yeah, so make your circles big.
One of our circles are filled in, right?
Well, maybe you could just kind of write it a little bit off to the side, but I want to see it because it's going to help you with your thinking process. Okay? So writing the electronegativity values in, I'm going to do the calculation now. Because if the difference is less than or is greater than or equal to 3.0, it is polar. So 4.0 minus 2.5 equals 1.5. So is this bond polar? Yes, it is. It's greater than it's not equal to, it's greater than 0.3. So yes. Now, if the bond is polar, I want you to draw the dipole arrow. We did this one day. And I want you to draw it along the length of the bond.
How do you know?
How do we know that again?
It is
Well,
more than
I'm going to explain it in just a moment. If these two bonds if this bond involves the sharing of electrons, with fluorine being more electronegative, it's going to have a stronger pull, a stronger attraction of the electrons that are being shared. So the dipole arrow is drawn along the length of the bond, and it is pointing into the direction of the element with the greater electronegativity. Okay? That's why I wanted you to write the values either in the circle if you've already drawn them and have enough room, or if you've already drawn them and don't have enough room, maybe off to the side like this. But put the value there so that it's a visual. how do I know where these electrons are going? They're going towards the one with a higher pull of electrons. All right, this bond is polar, without a doubt. What about this one? It's the same. So we have two polar bonds here. We will draw two dipoles.
So for like this one, you go the opposite way.
Yep, it was asked with this first one here, water, which ends up being a bent structure. Oxygen on the top has a value of 3.5 and hydrogen has a value of 2.1. So when you do the calculation, you end up seeing that it is polar. The arrow would be drawn toward, going upward toward the oxygen because it is a higher number.
So it'd be 3.5 times 2.1.
It would be 3.5 minus 2.1 for that calculation.
So if it's less than 0.3, do you still draw the arrows?
If it is, I'm just gonna put this category in here. If it is less than 0.29 and less, and you write no here, there is no arrow. Okay? So the goal today is for you to, I was hoping that you had the geometry code already at this point, to build the molecule. When you build it, I want you to show me. Even if you hold it up across the room, draw the shape, indicate the shape name, the shape angle, put the numbers, electronegativity values on there so you have some understanding of where these numbers are coming from. Tell me if the bonds are polar or nonpolar. If they are, draw the dipole. If they are not, there is no dipole drawn. So, Maddie, you had a question?
So like the first one, the arrows would be pointing to so.
Yeah, but the one on the paper, the arrows are pointing.
For the very first one on the paper, it's water. I can switch it up a bit, and the hydrogens are down here, right, and the oxygen is there. Hydrogen is 2.1, oxygen is 3.5. So on that one, the arrows will be pointing up toward the oxygen because it's the bigger number. McKenna?
You don't draw the lone pair on.
You do not have to draw the lone pair because when you build the molecule, you're not going to see anything having to do with the lone pair. Some people feel better if they represent it somehow, so they'll like stick a couple lone pairs on there, or kind of like the drawing on the diagram that I gave you. But the fact is, I know that you know there are lone pairs by looking at both this and the Lewis structure. Katie, did you have a question?
That was my question.
Okay. I want to tell you that the single bonds are represented by sticks. The double bonds are represented by springs. So oxygen is a diatomic molecule with a double bond between it. I'm going to show you in the model kit what the double bond looks like. It involves two springs and actually gets connected like this. Okay? If you want to indicate a double bond on your molecule, you could draw two bonds like that. This would be a trigonal planar, but it is not necessary. Okay? It is not necessary to do that. But when you build it, if it has a double bond, I want to see the double bond.